Welcome to Chemistry Solutions with Steve. This is a walkthrough exam paper and it's the 2019 Chemistry Higher Paper 1 and it's the single science. You can download all exam papers from the AQA website, and if you just look at the link below, you can follow that straight to that site. This can be used by teachers and students. For teachers, perhaps who are not specialists in science, or perhaps are science teachers but not specialists in chemistry. Students, you can use it in a variety of ways. You can print a paper copy and fill it in, stop the video at certain points, rewind, etc. You can sit the exam in one full sitting and then go back and replay, mark it yourself. The choice is yours. So we'll start with some general exam advice. You'll be given the exam and you'll be able to look at the front page and go through that front page before the examination continues. And what I suggest you do is go through each of the bullet points on the front page and you tick it when you've read it. You know, use a pencil and just tick each bit when you've read it. And that way you know that there's no information that's going to be any surprise. Another piece of equipment that you might find useful is a highlighter pen, and this will help you to highlight key words, command words, and number of marks available for each question. So I'll demonstrate this now. Question 1. This question is about the periodic table. In the 19th century, some scientists tried to classify the elements by arranging them in order of their atomic weights. Figure 1 shows the periodic table Mendeleev produced in 1869. His periodic table was more widely accepted than previous versions, and here's figure 1 here. So we'll have a quick look at that. The atomic weight of tellurium, Te, is 128, and that of iodine is 127. Why did Mendeleev reverse the order of these two elements? And this is for 1 mark. So let's look at figure 1. Here's tellurium, look, and here's iodine. They were obviously swapped over before Mendeleev changed them. And if we look at this group here, what's in this group here? We've got bromine, chlorine, fluorine. They're all similar properties. They're all the halogens that we know today. So to get 1 mark for this question, we must say Mendeleev swapped them, so the elements iodine and tellurium were in groups with similar properties. For example, bromine, chlorine, fluorine in the case of iodine. Over the page, question 1.2. Mendeleev left spaces marked with an asterisk. He left these spaces because he thought missing elements belong there. Why did Mendeleev's periodic table become more widely accepted than previous versions? And this is for 3 marks. Well, let's look at that middle sentence. He left those spaces where he thought those elements would be because he predicted that they had similar properties to other elements in those groups. Secondly, later on, these elements were actually discovered and filled those gaps. And finally, the properties of those elements which he predicted matched the actual properties of the elements that were discovered. So, to claim the 3 marks, Mendeleev predicted the properties of these missing elements. Later on, these elements filled the gaps and their properties were the same as he had predicted. 1, 2, 3 marks, back of the net. 1.3. Mendeleev arranged the elements in order of their atomic weight. What is the modern name for atomic weight for 1 mark? Tick 1 box. Is it atomic number, mass number, relative atomic mass, or relative formula mass? And of course, the answer is it's the relative atomic mass for 1 mark. 1.4. Complete the sentence for 1 mark. In the modern periodic table, the elements are arranged in order of, and of course the answer is atomic number or proton number. Over the page. Chlorine, iodine and astatine are in group 7 of the periodic table. 1.5. Astatine 80 is below iodine in group 7. Predict the formula of an astatine molecule and the state of an astatine molecule at room temperature. And this is for 2 marks. So if we look at group 7, which is where we're talking about, it says at the top of the question, we know group 7 molecules all form diatomic molecules. In other words, a formula X2, 2 atoms in one molecule. So for the first mark, the formula is AT2. So if we go down the group, we know at room temperature, fluorine is a gas, chlorine is a gas, bromine a liquid, iodine a solid. So it stands to reason that astatine will also be a solid. So for the second mark, we write state at room temperature, solid. 1.6. Sodium is in group 1 of the modern periodic table. Describe what you would see when sodium reacts with chlorine for 2 marks. And the key word is, what would you see? So you're going to see a flame, a bright white flame. You're going to see some sodium chloride made. But you can't say that. Sodium chloride is a white solid, so you see a white solid. And finally, the green or the pale yellow colour of chlorine will gradually fade as it gets used up in the reaction. So any 2 from 3, a bright white flame, a white solid formed, the pale colour, yellow colour of the chlorine gas fades. Any 2 for 2 marks. The page, question 2. This question is about acids and alkalis. 2.1. Which ion do all acids produce in aqueous solution for 1 mark? Tick 1 box. Is it hydrogen? We think it will be. Let's have a look at the others. H minus, O2 minus, OH minus. Yeah, it's the top one. H plus, the hydrogen ion. 2.2. Calcium hydroxide solution reacts with an acid to form calcium chloride. Complete the word equation for the reaction for 2 marks. And you can see here you've got to complete what the acid is in the gap, first gap, and what the other product is on the right hand side there. Now this, it is a acid alkali or alkali acid reaction, and an alkali and an acid always give a salt plus water. So if we just write water there on the right hand side, that's our first mark. So the product on the right hand side is water. So to name the salt, we look for to name the acid, we look at the salt, calcium chloride. A chloride is always formed from hydrochloric acid. So in the first gap, hydrochloric acid. So 1 mark for hydrochloric acid, 1 mark for water. So, over the page, a student investigates the volume of sodium hydroxide solution that reacts with 25.0 cm cubed of dilute sulfuric acid. Figure 2 shows the apparatus the student uses. You can see figure 2 there, there's all the different bits which we'll come back to later. Use figure 2 to answer questions 2.3 and 2.4. Question 2.3. Name apparatus A. So let's go and have a look at it. And you will remember the name of this piece of kit is a burette. For 1 mark. 2.4. What is the reading on apparatus A? For 1 mark. Okay, so let's go back up again and have a look at the reading. Here's the level of the liquid, and you'll notice that the numbers go increasing downwards, and that's how a burette works. So we've got 27 and it goes down to 28. So if we look at that little mark there, we can count the number of individual marks, and that works out at 27.6. So we write 27.6 in the space provided for 1 mark. Page 2.5. The higher the concentration of a sample of dilute sulfuric acid, the greater the volume of sodium hydroxide needed to neutralize the acid. The student tested 2 samples of dilute sulfuric acid, P and Q. Describe how the student could use titrations to find which sample, P or Q, is more concentrated. And this is a 6-mark question. It's also a levelled response. So, to get level 3, which is 5 or 6 marks, the design plan would lead to the production of a valid outcome. All key steps are identified and logically sequenced. So let's take a look at figure 2 to see what information we can glean from what's already been given us. We've got the sodium hydroxide in the burette. We've got a conical flask in which we put our dilute sulfuric acid. So we can start by using those. Now we're going to use a pipette to get the acid into the conical flask, which is a exactly measured 25 centimetres cubed, and we're going to put some indicator into our acid, some phenolphthalein. That's a good one to use. So let's crack on. Measure, using a pipette, 25 centimetres cubed sulfuric acid P into the conical flask and add a few drops of phenolphthalein indicator, which will go colourless. Place the flask onto a white tile and top up the burette with sodium hydroxide to the 0 mark. We use a white tile to show the contrast in the colours, and the colour changes. It really helps. Now you're going to run the acid slowly into the flask. Swirl in the flask now and again and stop when the indicator goes pink. This is what we call a rough titration. We record the volume of sodium hydroxide added, and then we repeat this, but this time run the sodium hydroxide to within about 5 cubic centimetres and then add it more slowly. As the volume gets close to the first titration, we add 1 drop at a time until the solution turns pink. Now it's important to remember that you get your eye level with the meniscus in the burette, and there's a diagram to show you that. And then we repeat this to get 3 concordant results. Concordant just means they're very close to each other, usually about 0.1 centimetres cubed, and then we calculate the mean average. Now finally we repeat the whole process for acid solution Q. And then we compare the 2 average titers for P and for Q. The titration that used more sodium hydroxide was the one that had to work and react with the more concentrated acid. 6 marks, back of the net. This question is about materials and their properties. Figure 3 shows a carbon nanotube. The structure and bonding in a carbon nanotube are similar to graphene. Carbon nanotubes are used in electronics because they conduct electricity. Explain why carbon nanotubes conduct electricity for 2 marks. Now graphene has only got 3 bonding electrons, so this question is about delocalized electrons. So the carbon nanotube contains delocalized electrons which can move throughout the structure and carry the charge. 1 mark for delocalized electrons, 1 mark for moving and carry the charge. And don't forget, this is an explain, so we've got that linking word which. Question 3.2. Figure 4 shows a badminton racket. Table 1 shows some properties of materials. The materials could be used to make badminton racket frames. So here you've got table 1, you've got the list of materials, and then the 3 properties: density, relative strength, relative stiffness. Evaluate the use of the materials to make badminton racket frames. And this is a 4-mark question. It's also a levelled response, and for level 2, which is to 3 or 4 marks, some logically linked reasons are given, but there may also be a simple judgment, hence the evaluate. Let's look at density. Wood is light because it's got a density of 0.71 grams per cubic centimetres, whereas aluminium looks too heavy, that's 2.7 grams per cubic centimetres. Relative strength, we can see here the carbon nanotube is much stronger and therefore would be the preferred one, and the aluminium and wood are much weaker. So the wood and the aluminium could break if they are used too strongly. Finally, relative stiffness, the carbon nanotube has got a factor of 1,000, which could make sure that it was strong and wouldn't bend out of shape. However, aluminium and wood could be flexible if that's a requirement of a badminton racket. So by making some notes on the table, we can begin to put our answer into that logical order, and at the end then come up with a decision. Wood frames are least dense, so would be lighter to use and easier to make shots. Aluminium is most dense, so will be heavy to wield. Carbon nanotubes are strongest, so least likely to break, whereas the weaker wood and aluminium would break more easily. The carbon nanotube is the stiffest, so less inclined to bend out of shape. Wood and aluminium are not very stiff, so they could distort. However, could be more flexible if that was required. Overall, I would choose carbon nanotube as it's both strong and stiff, yet has a medium density. Over the page. Zinc oxide can be produced as nanoparticles and as fine particles. 3.3. A nanoparticle of zinc oxide is a cube of size 82 nanometers. Figure 5, and here's figure 5 below, represents a nanoparticle of zinc oxide. Calculate the surface area of a nanoparticle of zinc oxide. Give your answer in standard form for 3 marks. Each side of the cube has a length of 82 nanometers. So, to calculate the area of one side or face, we have to multiply 82 by 82. There are 6 faces to the cube, so that means we have to multiply 82 by 82 by 6. So if we lay out our calculation, one side is 82 nanometers by 82, which is 6,724 nanometers squared. 6 times 6724, 40,344 square nanometers, beg your pardon. Now let's put this into standard form. About 1, 2, 3, 4, that gives us 10 to the power of 4. And to 2 significant figures, our final answer, 4 times 10 to the power of 4. So 1 mark for working out the area of one face, 1 mark for the actual answer for 6 faces, and then a final mark is for our answer in standard form. 3.4. Some sun creams contain zinc oxide as nanoparticles or as fine particles. Suggest one reason why it costs less to use nanoparticles rather than fine particles in sun creams. And this is a 1 mark question. These questions are often about particle size and surface area to volume ratio. So to get the mark, because of the smaller particle size, you would use less, or you could say nanoparticles have a greater surface area to volume ratio. 1 mark. Over the page, question 4. This question is about atomic structure. 4.1. Atoms contain subatomic particles. Table 2 shows the properties of 2 subatomic particles. Complete Table 2 for 2 marks. Subatomic particles is something you should recall from very early on in your course. A neutron has a relative mass of 1, and the word neut stands for neutral or relative charge 0. Now, there's only one positive charge in a nucleus, and that is a proton. And if you remember, P always stands for plus. P for plus. So the name of the particle is a proton. And as we know, neutrons and protons both have a relative mass of 1. So it's 1 mark for mass of 1 and charge 0 for neutron, 1 mark for proton, and 1 for the relative mass. An element X has 2 isotopes. The isotopes have different mass numbers. 4.2. Define mass number. Now, if we look at the symbol for carbon from the periodic table, which is a big C with a 12 at the top and the 6 at the bottom, the 12 is what we call the mass number. So it tells you that the mass number is the total of number of neutrons and protons in the nucleus. So for 1 mark, you must write the number of protons and the number of neutrons. Question 4.3. Why is the mass number different in the 2 isotopes for 1 mark? Now this is another way of asking you, do you know what a definition of an isotope is? And remember, isotopes are 2 atoms of the same element with a different number of neutrons. Over the page. Question 4.4. The model of the atom has changed as new evidence was discovered. The plum pudding model suggested that the atom was a ball of positive charge with electrons embedded in it, like the fruit in a pudding. Evidence from the alpha particle scattering experiment led to the change in the model of the atom from the plum pudding model. So let's just highlight some of the key phrases, and remember we have to explain how this model took over for 4 marks. Explain how. And this is a 4-mark question. This is a question you often get, and basically it's asking you to compare the two models. Now let's have a quick look at the alpha particle scattering model here on the left hand side. What Rutherford did was he got a thin leaf of gold foil and he fired alpha particles at it, and what he found was most of the alpha particles, i.e. the black lines, went straight through the foil. 1 or 2 were deflected at an angle and 1 or 2 were bounced straight back. So let's see what this means. In the scattering experiment, most of the alpha particles passed through the gold foil. This means, and that's a key word for explaining, this means that most of the atom must be empty space, or you could say most of the mass is concentrated in the centre called the nucleus. Now alpha particles are positively charged, so as they approached the centre of the atom, because they were deflected or reflected, the centre of the atom must have a positive charge, and that's what Rutherford also found out. So to finish off for the last 2 marks, a few alpha particles were bent or bounced straight back. This means, there's that phrase again, the centre of the atom must have a positive charge. And you can see here where we've allocated the marks. In scattering, alpha particles pass through 1 mark, empty space 2 marks, bouncing back 3 marks, positive charge, and then that's our 4th mark. Over the page for question 5. This question is about ammonia, NH3. 5.1. Complete the dot and cross diagram for the ammonia molecule shown in figure 6. Show only the electrons in the outer shell of each atom, and this is a 2-mark question. So here's figure 6, something you must have done dozens of times in your lessons, the good old dot and cross diagrams. The hardest part is knowing how many electrons to put in. So if you think back to the periodic table, nitrogen is in group 5 of the periodic table, and therefore it's got 5 outer electrons in its outer shell, 5 electrons in its outer shell. Hydrogen, we know, has only got 1, so that's our starting point. Let's do the hydrogens first. So we put 1 hydrogen in each of the overlaps, and I prefer to put mine actually on the shell or the circle around the hydrogen, then I know where it's come from. Now in a dot and cross diagram the electrons must be shared, so in red I've put the 3 electrons that must be shared with the 3 hydrogens, and I've put those on the ring, on the circle, the energy level around nitrogen. So now if we count up, we've got 6 electrons, 2, 2 and 2. Now we know the octet rule, every atom must have a full outer shell of 8, and it forms its covalent bonds. So there are 2 missing, so we put our 2 electrons at the top in red, and we call these a lone pair. 1 mark for the 3 bonding pairs and 1 mark for the lone pair at the top. 5.2. Give 1 limitation of using a dot and cross diagram to represent an ammonia molecule. This is a common question. You're often asked to contrast and compare different models of representing molecules and bonding, and you can pick any one of these from 3. It doesn't represent the shape or the bond angles, there's no 3D representation, and there's no scale or size. Any one for 1 mark. 5.3. Explain why ammonia has a low boiling point. You should refer to structure and bonding in your answer, and this is a 3-mark question. So let's look at this model of an ammonia molecule. The molecules are the blue ovals, and you can see the little lines between them, and these represent weak intermolecular forces between the molecules, inter being between. Within the molecule, the black lines represent very strong covalent bonds, and these substances, these molecular substances like ammonia, have only weak forces between the molecules. As we say, we call these intermolecular forces. And it is these that are overcome when there's a change of state, not the covalent bonds. And with this type of question, you should only use this phrase intermolecular forces or weak intermolecular forces. I used to call it whiffies with my students. It's just a way of trying to get them to remember it. So let's construct an answer. Ammonia is a small covalently bonded molecular substance, 1 mark. The molecules have only weak intermolecular forces, 1 mark, between them. When heated, these intermolecular forces are easily overcome. And here we go again. Boom. Therefore, for that explain, little energy is required to overcome these forces. 3 marks, back of the net. Over the page, 5.4. Ammonia reacts with oxygen in the presence of a metal oxide catalyst to produce nitrogen and water. 5.4. Which metal oxide is most likely to be a catalyst for this reaction? This is for 1 mark. Tick 1 box. So let's go down the list. They're all oxides. When we're looking at catalysts, we're looking for transition metals. Now the first one, calcium, group 2. Second one, chromium, could be. Third one, magnesium, no, that's group 2 as well. Fourth one, sodium, group 1, no, so it's got to be the second one down, the chromium oxide. So tick the chromium oxide box for 1 mark. Figure 7 shows the displayed formula equation for the reaction. Table 3 shows some bond energies, and here we are. We'll look at these in a minute, table 3. Now look at the equation. What you can see in this equation are the covalent bonds, the bonds between nitrogen and hydrogen, the oxygen-oxygen bonds, the nitrogen-nitrogen bonds, which happens to be a triple, and the hydrogen-oxygen bonds in water. Question 5.5. Calculate the overall energy change for the reaction and use figure 7 and table 3, and this is a 3 mark question. Now these are best approached by using the table method. So we construct a little table. You don't have to draw it as neat as that, but you want your bonds broken on the left hand side and bonds made on the right hand. Then we go up to figure 7, and we can see that in figure 7 there are 3 bonds between nitrogen and hydrogen. So in each molecule there are 3 bonds, and then there are 4 molecules. So that must give us overall 12 NH bonds. There's 1 double oxygen bond in a molecule of oxygen, and there are 3 molecules. That gives us 3 OO bonds. Nitrogen's got 2 triple bonds, and if we look at the oxygen molecule, in each molecule of water there are 2 OH bonds. There are 6 molecules. That gives us 12 bonds overall. Then we just put this information into the table. 12 times NH equals 12 times 391 equals 4692. 3 lots of OOO gives us 3 times 498, which is 1494. Add these two together and we get 6186 kilojoules of energy used to break the bonds in the equation. Now let's look at the bonds made. We've got 2 nitrogen triple bonds, so that's 2 times 945 equals 1890. 12 OH bonds equals 12 times 464 equals 5568. Then we add these two together, that comes to 7458. So this is the energy released when all the bonds on the right hand side of the equation have been made. So in order to calculate the overall energy change, we're going to take the energy from the bonds made and take it away from the bonds broken. So overall energy change equals energy of bonds broken, take away energy of bonds made. So that's 6186, take away 7458. When you crunch all that on your calculator, you get minus 1272 kilojoules. You get a mark for calculating bonds broken, mark for calculating the energy for bonds made, and then the final mark for the sum to get the final answer. Question 5.6. Explain why the reaction between ammonia and oxygen is exothermic. Use values from your calculation in question 5.5 for 2 marks. So let's look back at that table and that calculation. The bonds broken is 6186, bonds made 7458. The overall energy change is a negative value. So what does that tell us? Here we can construct our answer. In 5.5, the energy released in making new bonds, 7458 kilojoules, is greater than the energy used to break bonds, 6186. Therefore, energy is released to the surroundings, which means it's an exothermic reaction. Over the page, 5.7. Figure 8 shows the reaction profile for the reaction between ammonia and oxygen. Complete figure 8 by labelling the activation energy and the overall energy change for 2 marks. So the activation energy is shown by drawing a line across straight away from the reactants and then onto the peak of the graph, a line across there, and that peak is known as the activation energy. The overall energy change is the difference from the level of the reactants down to the level of the products, and then it's been labelled there. So 1 point for activation energy labelled correctly, 1 point for overall energy change labelled correctly. 2 marks. For the page, this question is about chemical cells. Question 6. A student investigated the voltage produced by different chemical cells. Figure 9 shows the apparatus, and here's figure 9. You've seen this before, probably done several experiments like this. You've got a voltmeter, some electrodes, and an electrolyte solution. This is the method used. There's the method 1, 2, 3. Cobalt is electrode X, and then you record the cell voltage, repeat steps 1 and 2 with different metals. Question 6.1. Suggest 2 control variables used in this experiment for 2 marks. Now, control variables, remember, are the factors you have to keep the same in order to gain valid results. So we're going to have to look at the solution, the concentration of the solution, the electrolyte, that should be kept the same, as should the temperature of that solution. And you must use the same solution throughout the whole of the experiment. And it's always a good idea to have the same size and surface area of the electrodes. So any 2 of those for 2 marks. Moving on, Table 4 shows the student's results, and here's Table 4. You've got the results for electrode X and the measurement of voltage of each cell in volts. So cobalt plus 0.62, copper is 0, magnesium 2.71, nickel plus 0.59, silver minus 0.46, and tin plus 0.48. 6.2. Write the 6 metals used for electrode X in order of reactivity. Use Table 4 and justify your order of reactivity. So the metals are compared with copper, and the metals with the highest voltage difference, or the highest voltage, are going to be the most reactive. So looking at Table 4, we can see magnesium is the most reactive because it's plus 2.71. Then we've got cobalt, followed by nickel. And then in number 4, we've got tin. 5 is copper, because copper with copper as an electrode, both the same, can't have any voltage because they're both the same metals. And this is a key point here. The last one, number 6, is silver, because silver is negative 0.46, and obviously that's below copper because that's below 0. So for 2 marks, there's your list of most reactive: magnesium, cobalt, nickel, tin, and that's 1 mark, and then the second mark, copper, finally silver. Now we've almost answered the justification. The biggest voltage occurs when the difference in the reactivity of the 2 metals is the largest. A cell made from magnesium and copper has the highest voltage. So the higher the voltage, the more reactive the metal. Silver is the least reactive because its voltage difference is negative, i.e. it's less than copper. So we get 1 mark for saying the higher the voltage, the more reactive the metal, and the second and eventually 4th mark will be the silver is the least reactive because its voltage difference is negative, and that's important. When this was answered, not many students got that correct. 6.3. Which of the following pairs of metals would produce the greatest voltage when used as electrodes in the cell? And use table 4. Tick 1 box for 1 mark. So the 4 choices you've got are magnesium and cobalt, magnesium and tin, nickel and cobalt, nickel and tin. Our final answer must involve magnesium because it is the biggest voltage. So that means we can concentrate on the first 2. And if we look at magnesium and cobalt, we can have a little sum here. 2.71 take away 0.62 gives us 2.09. Magnesium and tin, 2.71 take away 0.48 gets 2.23. So magnesium and tin give us the largest voltage difference, so we tick a box for 1 mark, magnesium and tin. 6.4. Hydrogen fuel cells can be used to power different forms of transport. Some diesel trains are being converted to run on hydrogen fuel cells. A newspaper article referred to the converted trains as the new steam trains. Suggest why? For 2 marks. Now, a suggest means there could be a number of answers and there's no definitive answer. They're looking for you to use your imagination a little bit. So, what do we know about a fuel cell? Well, in a fuel cell, hydrogen reacts with oxygen and the product is water. And this is often produced as steam, hence the reference to steam trains. So, to get 2 marks, the overall reaction in a hydrogen fuel cell involves the oxidation of hydrogen to produce water. Hydrogen plus oxygen gives water. That's a mark. And the water is released, the water produced is released as steam. 2 marks. Question 7. This question is about electrolysis. Aluminium is produced by electrolyzing a molten mixture of aluminium oxide and cryolite. Question 7.1. Explain why a mixture is used as the electrolyte instead of using only aluminium oxide for 2 marks. The use of cryolite in the manufacture of aluminium is one of those things you just have to learn it. Now, what cryolite does, cryolite has this ability to lower the melting point of the aluminium oxide. And what this means is we can use less energy, which is good for all sorts of reasons. Now, in this exam, for real, not many people got this question right. And a lot of people tended to think that cryolite was a catalyst or that it reduced costs. Please do not mention costs as an answer. 7.2. What happens at the negative electrode during the production of aluminium? Tick 1 box for 1 mark. 4 choices. Aluminium atoms gain electrons, aluminium atoms lose electrons, aluminium ions gain electrons, aluminium ions lose electrons. Now we know electrolysis must involve the discharge of ions. So the first 2 answers have got to be incorrect. The answer's got to involve aluminium ions. What else do we know about an aluminium ion? Well, aluminium is a metal. All metal ions are positive. So we're looking for aluminium ions doing something. To become aluminium metal, they must gain electrons. So therefore, we're looking at the 3rd choice. So to get 1 mark for this question, aluminium ions gain electrons. 1 mark. 7.3. Oxygen is produced at the positive electrode. Complete the balanced half equation for the process at the positive electrode, and this is for 2 marks. Now, we know oxygen is in group 6 of the periodic table. It must therefore form an O2- ion. So that's the first thing we write in there. On the left-hand side of the arrow, O2-. On the right-hand side, there are 2 oxygen molecules repeat, 2 oxygen atoms in the oxygen molecule. So now we must balance the number of oxygen ions. So we put a 2 in front of O2 minus. In a half equation, we must either add or lose electrons. Now we know oxygen 2 minus has got 2 extra electrons in its outer shell. So when it forms an oxygen molecule, it will lose these 2 electrons. Now because there are 2 ions, 2 times 2 makes 4. So on the right hand side we must put 4 electrons. So 1 mark for the 2 O2 minus, 1 mark for 4 E minus. Over the page, question 7.4. Explain why the positive electrode must be continually replaced for 3 marks. This is something that comes up now and again, but it is in the syllabus and it is worth remembering. So let's have a look at this. Look back at question 7.3. Oxygen is produced at the positive electrode. So there is bubbles of oxygen being produced in this electrolytic cell, which is extremely hot, over 1,000 degrees. The electrodes are made of carbon, so you've got a hot environment with carbon and oxygen. It's going to make carbon dioxide. The carbon will react with the oxygen to make carbon dioxide. So this way, the carbon will gradually be worn away, and so therefore that's why they have to be replaced. So let's look at the marks. The positive electrode or anode is made of carbon, 1 mark, which reacts with the oxygen, 2 marks, to produce carbon dioxide. That's your 3rd mark, and that's why it must be replaced. 7.5. The overall equation for the electrolysis of aluminium oxide is 2Al2O3 goes to 4Al plus 3O2. Calculate the mass of oxygen produced when 2,000 kilograms of aluminium oxide is completely electrolyzed. And you've got the relative atomic masses of oxygen and aluminium, and this is a 4-mark question. This is one of those reacting masses. So let's use my table method. It works every time. It looks a bit clumsy, but if you follow the steps, it works every single time. Let's extract from the question the bits we need. We only need to be thinking about the aluminium oxide and the oxygen, because that's what's in the question. We're calculating the mass of oxygen. And we're going to use a good old formula triangle, Mr. Moles with the mass on his head. So we put down the left-hand side, the mass, Mr. Mole, and the other thing we need is the ratio. That's the key to this one, the ratio of molecules involved. So we can sub in some numbers. The mass is 2,000 kilograms. Normally you do it in grams, but if we keep it in kilograms, the answer will be the same in kilograms. Now the Mr. for aluminium oxide is on the left here, 27 plus 27 plus 3 lots of 16, 102. So we go to our formula triangle. We need the moles now of the aluminium oxide, so we're going to divide 2,000 by 102, and that gives us 19.6 whatever. You can see the numbers there. Keep them on your calculator and don't press clear. We go to the equation now to get the ratio. So the ratio is for every 2 aluminium oxides there are 3 oxygens. So we must multiply our moles by 3 and divide by 2. And here's the answer on the calculator. Again, leave it on the calculator because you're going to need it in a minute. The answer is 29.41 and all those numbers. Now we go up for the the Mr. of oxygen. Oxygen is O2, so it's 16 plus 16, 32. Back to Mr. Moles with a mass on his head. The mass of oxygen is going to be 32, the Mr, times the mole, that 29.4 long number that's on your calculator. Crunch that and you should get your final answer, 941.la-di-da-di-da, which we're going to round up to 3 sig figs, 941 kilograms of oxygen produced. 4 marks. 1 mark for the Mr. of aluminium oxide, 1 mark for the moles of aluminium oxide, 1 mark for the moles of oxygen, and the final mark for the actual final answer of 941. 4 marks. Works every time. Over the page, sodium, metal and chlorine gas are produced by the electrolysis of molten sodium chloride. 7.6. Explain why sodium chloride solution cannot be used as the electrolyte to produce sodium metal. This is for 2 marks. You must recall that in a solution you have extra ions. You have H plus and OH minus ions. So, in sodium chloride, hydrogen ions are discharged in preference to sodium ions. And the reason for this is the sodium is more reactive, so the hydrogen ions are preferentially discharged. So, for 2 marks, in a solution there are H plus ions, so these H plus ions would be discharged in preference to Na plus. Sodium. Here we are, and we've underlined that keyword again because it's an explain question, because sodium is more reactive than hydrogen. 2 marks. 7.7. Calculate the volume of 150 kilograms of chlorine gas at room temperature and pressure. The volume of 1 mole of any gas at room temperature and pressure is 24.0 decimeters cubed. You've got the formula masses for chlorine there, 71, and it's a 2-mark question. In most of these calculation type questions, you need to work out the moles of something. So we've got 150 kilograms of chlorine gas. So using Mr. Moles with the mass on his head, we need to divide the mass, 150 kilograms, by the Mr., the MR, which is 71. This time we must convert the kilograms to grams, so we've got 150,000 grams divided by 71, and that equals 2,113 moles of chlorine gas. 1 mole is 24 decimeters cubed. So therefore we must multiply the number of moles by 24.0 decimeters cubed. When you crunch that on your calculator, you get 50700. 1 mark for the number of moles, 1 mark for the final answer, 50,700 decimeters cubed. Question 8. Copper forms 2 oxides, Cu2O and CuO. A teacher investigated an anoxide of copper. Figure 10 shows the apparatus, and here's figure 10. You've got these 2 glass tubes joined by a thin tube, and you've got tube A where you've got some hydrogen going through some oxide of copper, which is heated. Then into tube B there's some drying agent, and at the end excess hydrogen burning. This is the method used. Weigh empty tube A, add some of the oxide of copper to tube A, weigh tube A and oxide of copper, weigh tube B and drying agent, pass hydrogen through the apparatus and light the flame at the end, heat the tube A for 2 minutes, reweigh tube A and contents, repeat steps 5 to 7 until the mass no longer changes, reweigh tube B and contents, repeat steps 1 to 9 with different masses of the oxide of copper. 8.1. Suggest one reason why step 8 is needed, and this is for 1 mark. Now if you look at step 8, it's asking you to keep weighing until the mass doesn't change anymore, and this is important because once the mass has stopped changing, the oxide has stopped reacting. So to get 1 mark for this question, you must write in the space provided to make sure all of the oxide of copper has reacted. And I've just put in brackets there, when no more reacts, the mass will be constant. 8.2. Explain why the excess hydrogen must be burnt off. Now, what do we know about hydrogen? Highly flammable, highly explosive. So we don't want our labs filling with lots of hydrogen, do we? No, thank you. So for 2 marks, hydrogen is explosive. Hydrogen gas is explosive. Therefore, and that's our explain get out, it is important not to let any excess hydrogen escape into the air. 2 marks, boom. Now, over the page, and it's just repeating figure 10 here, and it saves you having to go back 2 pages to find it. Table 5 shows the teacher's results, and here's a list of results of all the different tubes and all the weights and masses here down the other side. I'm not going to read them all out, but I'll pause it and you can have a look at that yourselves. When an oxide of copper is heated in a stream of hydrogen, the word equation for the reaction is copper oxide plus hydrogen goes to copper plus water. So over the page, 8.3, determine the mass of copper and the mass of water produced in this experiment. Use table 5 for 2 marks. So if we look at figure 10, tube A has started with copper oxide in it and now there's just copper. So if we look down the table, we're looking to try and find if we can work out the mass of copper, and we're going to find that by looking at tube A empty and tube A and contents after 6 minutes, because after 6 minutes the mass hasn't changed, so the reaction is finished, so it should be just copper. So on our calculator we need to crunch 114.38, take away 105.72. So here's the calculator now. So we're going to key in 114.38 minus 105.72 gives us 8.66. So here's the sum in the answer space. The next part then, calculate the mass of water produced in the reaction. So we go to figure 10. We can see the drying agent there, and that's absorbing the water coming through from the reaction. So we're looking for the tube B contents at the start and tube B contents at the end, and we're going to take the contents of B away from B at the end away from B at the start. That's 123.93. 123.38, take away 120.93. So here comes the calculator. 0.38, take away 120.93, and that gives us 2.45. So if we go to the answer grid, the sum's already written out there, and the answer is 2.45. So 1 mark for the mass of copper, 1 mark for the mass of water. The teacher repeated the experiment with a different sample of the oxide of copper. The teacher found that the oxide of copper produced 2.54 grams copper and 0.72 grams water. Two possible equations for the reaction are equation 1, Cu2O plus H2 goes to T2Cu plus H2O. Equation 2, CuO plus H2 goes to Cu plus H2O. Determine which is the correct equation for the reaction in the teacher's experiment. Relative atomic masses are given there, and this is for 3 marks. This is an adaptation of the reacting mass type calculation. And it's all about moles. So we're going to use a very similar framework here. We're going to use Mr. Moles with the mass on his head, and we're also going to use the table method. In previous calculations, we used the mole ratios to work out the missing mass. This time we're given both masses and we have to find the mole ratio. So on the left-hand side, there's Mr. Moles with the mass on his head, and we've got our 4 areas: mass, Mr. Moles, ratio. We've put copper and water at the top, the symbols and formulas. So let's sub in some of the details. 2.54 grams of copper. The MR for copper is 63.5, so to get the moles, we're going to divide the mass by the Mr. So that's 2.54 divided by 63.5. That comes out at 0.04. Over to water, 0.72 grams of water, so we write that in. The MR for water is 18. 16 plus 2 ones makes 18. And then we're going to divide it out. So 0.72 divided by 18 also comes out as 0.04. So we can see straight away the ratio here is a 1-to-1 ratio. So if we go back up to the 2 equations, the copper and hydrogen water exist in a 1-to-1 ratio in equation 2. So equation 2 is the right answer. 1 mark for working out each mole number and 1 mark for the final answer. Page for the final question, number 9. A student investigated the temperature change in the reaction between dilute sulfuric acid and potassium hydroxide solution. This is the method used. 1. Measure 25 cubic centimetres potassium hydroxide solution into a polystyrene cup. 2. Record the temperature of the solution. 3. Add 2 centimetres cubed dilute sulfuric acid. 4. Stir the solution. 5. Record the temperature of the solution. 6. Repeat steps 3 to 5 until a total of 20 cubic centimetres dilute sulfuric acid has been added. 9.1. Suggest why the student used a polystyrene cup rather than a glass beaker for the reaction. This is a question about insulation and heat loss. A glass beaker is a much more conductive material for heat energy. Polystyrene cup will keep the heat energy in and therefore make the readings more valid and accurate. So to get 2 marks, polystyrene has a better insulating properties and therefore less heat will be lost to the surroundings. Shows some of the students' results, and here we are. We've got a column that says volume of dilute sulfuric acid in centimetres cubed, and the second column temperature in degrees C. And if you go down, the volumes are going up by 2 centimetres each time, and you can see here a range of temperatures going up. We're going to come back to these in a moment. Figure 11, that's the graph, shows some of the data from the investigation. So you've got a partly drawn line here. 9.2. Complete figure 11. Plot data from table 6. Draw a line of best fit through these points. Extend the lines of best fit until they cross. This is for 4 marks. I'm sure you've done many graphs like these before. I've got the table of results. I've copied it and posted it down here. And go through, and each time you put a plot on, tick it off, then you know you've not missed any out or done any twice. And we'll see the line of best fit emerge. Now, drawing a line of best fit on a computer is almost impossible, but on a graph paper, use a nice sharp pencil, preferably a mechanical one. It has a very, very fine nib, and do distinct fine crosses for each plot. So there's my horribly squiggly line, but at the top you can see what was asked to do, and that was extend both lines so they cross over. So we have 2 marks for a correct plotting of the line, and 1 mark for a line of best fit, and then the 4th mark is for the crossing over of the 2 lines. 9.3. Determine the volume of dilute sulfuric acid needed to react completely with 25 cm cubed of the potassium hydroxide solution. Use figure 11 for 1 mark. So this is where we go back to the graph, and we need a ruler to draw a construction line. And I'm going to put my ruler in a vertical position on where the 2 lines cross over, and then draw down to the x-axis and put a pencil mark. And you can see that that pencil mark is on 11 cubic centimetres. So that's my answer, because when the 2 lines cross, that is when the reaction is finished, when the reaction is completed, and then the temperature starts to go down again. So in the answer space provided, we write 11. 9.4. Determine the overall temperature change when the reaction is complete. Again, use figure 11 for 1 mark. So we're looking for the minimum temperature, which is here in the table, 18.9, and we need to work out the maximum temperature. So again, we use our ruler to make a construction line. And once again, the reference is going to be where the 2 lines cross, which is the maximum temperature. Draw a pencil line across, and you can see that that number is there, 27.6. So in the space provided, we write 27.6. Take away 18.9 because we've got to get the temperature different. 27.6 take 18.9 gives us 8.7 degrees Celsius for 1 mark. (9.5) The student repeated the investigation. The student used solutions that are different concentrations from the first investigation. The student found that 15.5 centimetres cubed of a 0.5 mole per decimetre cube sulfuric acid completely reacted with 25 cm cubed of potassium hydroxide solution. The equation for the reaction is as below. 2KOH plus H2SO4 goes to K2SO4 plus 2H2O. Calculate the concentration of the potassium hydroxide solution in moles per decimetre cubed and in grams per decimetre cubed. The relative atomic masses are below. This is a 6-mark question and it's a titration calculation, and we can use another table method very similar to reacting masses, and I'll lead you through it now. Right, there's another formula triangle. This time it's called the NCV. Number of moles divided by concentration times volume. We also extract from the equation the bits that we need. If you look above at the question, we're only really looking at potassium hydroxide and sulfuric acid. So we write those out exactly as they occur with their mole ratios. Down the left-hand side, we write the concentration, the volume, number of moles, and the ratio. And then we sub in from the question the information we've already got. We work down, across, and back up. So, from the question, we know we've got 0.5 moles per decimetre cubed of the sulfuric acid. The reaction with the acid used up 15.5 centimetres cubed, but we've got to convert that to decimetres cubed because that's what the concentration is. So to convert centimetres cubed to decimetres cubed, we divide by 1,000. So 15.5 divided by 1,000, that comes to 0.0155. Over to the triangle now. To get the number of moles, we need the concentration times the volume. So 0.0155 times 0.5 equals 0.2075. Extracting from the equation, the ratio of sulfuric acid to potassium hydroxide is 1 to 2. So for every 1 mole of sulfuric acid, there are 2 moles of potassium hydroxide. So for the moles, we have to multiply that now by 2. That gives us 0.0155. Our ultimate goal is to calculate the concentration of the potassium hydroxide. So we look up to the stem of the question to get the volume of potassium hydroxide, and that is 25 cm cubed. Again, we must convert that into decimetres cubed, so we divide it by 1,000 and come up with 0.025. Back to the formula triangle, the concentration now is the number of moles divided by the volume, so that is 0.0155 divided by 0.025. Once you've crunched that in your calculator, you come up with 0.62. So there's 4 marks here. 1 mark for the moles of sulfuric acid, 1 mark for the ratio, 1 mark for the moles of potassium hydroxide, and the 4th mark goes for the concentration, 0.62. Now, for the second part, we have to convert moles per decimetre cubed to grams per decimetre cubed. And simply to do that, we just multiply the number of moles by the MR, the molecular mass. So that's 0.62 times 39 plus 1 plus 16. That comes to 56. So 0.62 times 56, 34.7 grams per decimetre cubed. 1 mark for calculating the MR of potassium hydroxide, 1 mark for the sum and final answer. 6 marks. Now follow the procedures step by step and practice these on the internet with some other types of questions very similar, and you'll soon get used to this. That's the end of this paper. Hope you got something valuable out of it. Go back over and look at those questions that you didn't do very well at. It's another successful video from Chemistry Solutions with Steve. Give us a like, usual things, and we'll see you in the next video.